Hi guys, welcome to another one of Untitled lectures, and today we'll be looking specifically at diffraction. Now this is a topic that is relevant to waves and it is part of the csec syllabus and more in-depth at the CAPE Unit 1 Module 2 level. Now when we talk about diffraction, we are first going to examine what is diffraction. But before we get into the meat of diffraction, I want us to talk a little bit about where diffraction comes from. Now diffraction is a property of a wave, and you can recall that a wave is a means of transporting energy. So you have different forms of a wave. You can have a wave carrying light energy, you can have a wave carrying sound energy. Now diffraction is a property where you have the wave being spread out when it passes through a gap or an obstacle. So a basic definition of diffraction is the spreading out of a wave when it encounters a gap, right? Now, if you think about opening a door, for example, and you are standing inside a room and you have the doorway open and somebody is standing outside and you are speaking, then the sound energy is able to diffract through the doorway and the person on the outside is able to hear you. Now, it's a little bit difficult if the person for the person to see you. And the reason for that is diffraction is maximum, that is, you have a maximum effect. You would have diffraction having a maximum effect if the size of the gap is comparable to the wavelength. Now sound waves have a much larger wavelength, so the size of a doorway, for example, is comparable to the wavelength of sound, which is why if you have somebody standing outside the door, you are able to hear them, right? Now the opposite is light, which has a much smaller wavelength, and because of that the size of the door is not comparable to have a majority spreading out occurrence. That is, it is very difficult to have a maximum pattern noted. Now it is not impossible, it's just that in a lab you can recreate a situation where you have a size of a gap or spacing that is comparable to the wavelength. So if we look, we can represent a wave as a series of parallel lines, and this is what you call a plane wavefront. Now the distance or the separation between the parallel lines is equivalent to the wavelength. This is because we consider the line to be a crest, the space to be a trough. So between alternate lines, you're going to have one wavelength. Now here, let's say you have a size of a gap, right? So we are talking about this value D being very comparable. So D is equal to lambda or thereabout, and we are going to notice what happens. And the effect is that you have maximum spreading out, and that is apparent by a change in the shape of the wavefront. So now you have maximum diffraction by the occurrence of a circular wavefront. Now again, the circular solid lines represent crests and the spaces in between represent troughs. So between alternate lines, you have the same wavelength being observed. Now nothing changes in diffraction except the shape of the wavefront, and that is indicative of the spreading out of the wave. Now on the other hand, if I had the same parallel wavefronts here and I have my gap, but guess what? The size of my gap, guys, is very large. So what I am going to notice is that just the edges, so let's actually make it a little bigger. So I want you to see the full, like what happens if you have very little spreading out. The body of the plane wavefront, that is the solid line, will pass through the gap, and it is just the edges that will tend to be curved as they pass through these parts here. But all in all, the wavelength is the same. That does not change. So this is minimum diffraction, and that will tend to occur where you have the size of the gap being greater than the wavelength. Now let's look at a specific experiment to observe diffraction, and that is called the Young's double slit experiment. Now the main purpose of this experiment is that it illustrates that light is a wave. Now you could recall from even concepts like the photoelectric effect that light is or travels in a straight line and it is made up of particles. And that being said, Thomas Young, Christian Huygens, these were scientists that worked to develop light is a form of energy and it's transmitted as a wave. What Thomas Young did was that he created two double slits and he allowed the light to diffract through each slit. And the diffracted beams underwent interference, where you had superposition of crest and crest, trough and trough to give you constructive interference, which is a larger waveform, or you had superposition of a crest and a trough, which resulted in the cancellation of the wave. Now, when that happened, you had destructive interference. And these destructive and constructive patterns were apparent in a series of alternate bright and dark fringes. Now, what happens with Young's double slit experiment is that you have to physically create in a lab a spacing, a slit spacing that is comparable to the wavelength. So what you will find is that if the wavelength is very small, then it is very difficult to have a naturally occurring slit, right? If we talk about everyday objects, like you're driving a car, you cannot see around a bend because obviously the size of that gap is much greater. Wavelength of visible light is about 4 by 10 to the minus 7 meters to 7 by 10 to the minus 7 meters. And because of that, it is very difficult to see diffraction, but it is not that it does not occur. So what he did is that he provided us in a lab situation where you had a spacing that was comparable to that wavelength. Now, there is a concept or a device called the diffraction grating, and many of the questions that come at the CABE level involve using that, right? So it illustrates light is a wave because light can be diffracted. So it showed that concept and interference occurs. Right, so let's look now at the device, but let's talk about the diffraction grating a little bit. So a lot of students get a little confused with it, right? But I want you guys to understand that the diffraction grating, it's basically a very small one, it's a square basically, right? And it has a very small dimension, for example 1 millimeter by 1 millimeter, and many times you have very large number of lines in that small spacing. So if I had, let's say, 6,000 lines per millimeter, it means that the spacing, I'm just going to shade it in yellow, that I am talking about for diffraction to occur would be obviously between the lines, right? So all of these yellows that I have shaded would represent the spacing between the lines, and that is the spacing that facilitates diffraction of light, because the size of that spacing is comparable to the very small wavelength of light. So now if we wanted to get the spacing, that is just 1 over the number of lines, right? So here, if I had said it was 6,000 lines per millimeter, then the spacing would be 1 over 6,000, and that will be per millimeter. You understand? And then you could have further divided that by 1,000 if you wanted to convert the value to meters. Okay? All right. So let us work now at the actual apparatus, right? So you had a source, and many times some people put a single slit to show that you just want to spread it out as much as possible to have a very prominent pattern, right? So essentially you're going to have your screen here where you are going to observe the pattern, you have your slit spacing. Your slits are S1 and S2, and they are a separation A apart. And you have the distance of the screen from these slits. We're going to call that capital D. And initially, I'm going to show a wave. So you're going to have your source here, right? And it produces the patterns, right? So you have your plane waves coming through. Now, what happens as it passes through the slit is that you're going to have a wave passing through the slit here. So we have 1, 2, 3, 4. So you have 4 cycles from S1. Now we're going to look at the 4 cycles as coming from S1 to the midpoint of the screen. And we're going to call that point O. So at the midpoint of the screen, a certain perpendicular distance between S1 and S2, we have O. Now, if I look at, because that distance is the same between S2 and O, and S1 and O, I will also have 1, 2, 3, 4. I will also, because of that distance, I will also have 4 cycles coming from S2 to O. So what I have here is always crest and trough overlapping. So just to revise, you are setting up a double slit, a certain distance, capital D, from a screen. I have labeled each slit position as S1 and S2. So I let the source produce the light so that it is incident on slits S1 and S2. I have considered a distance O as a distance at the center of my screen, which is the same perpendicular distance from S1 and S2. So S1O is equal to S2O. And therefore, I have considered 4 wavelengths to come from S1 and 4 to come from S2. And because they have the same number of cycles, when they meet at O, I will have constructive interference. And that is simply because I have the same, at any point, crest and trough will overlap because I have the same number of waveforms. That is what we consider as path lengths. So path length tells us how many cycles of wavelength I have at a point in time. And path lengths are analogous to phase differences, right? But we look at that just now. For now, understand that from S1 to O, I had 4 complete waveforms. From S2 to O, I have 4 complete waveforms. And what I notice is when these number of cycles overlap, I will always have constructive interference occurring. Now, at O, that is what you call your central maxima. Now, your central maxima is always where you have constructive interference. At any interference pattern, any fringe pattern, you have a centrally bright, we call that the zeroth order or the central maxima. Now, let us consider another point. Right, so let us consider another point just above O, right? And that is where, because you'll see O, and then that's centrally bright, and on either side, you're going to see darkness. Darkness is, because we're talking about light, a result of destructive interference. So you would want at a position just above and just below O to have points of destructive interference. So we're going to call that A prime, right? And we're going to call A prime as well. Right. So A prime is a point of destructive interference. So let's go. So let's say now I have a wave from S1, and because it's going to a point higher than O, we're going to look at this A prime, it will be more wavelengths, right? So let me just say you have 4.5. 1, 2, 3, 4, right. So I have 4.5 wavelengths, right? To go from S1 to A prime. Now, because S2 is further down, because A prime is all the way here, I would have to travel or have more cycles to get from S2 to A prime. So let's say I have 5. So I have 1, 2, 3, 4, 5. Right? Good. So now, when I have 5 wavelengths, S2A prime is greater than S1A prime. So I have 5 wavelengths compared to 4.5. So that means that at this point where they meet, right, based on how they overlap, they have a path difference of half a wavelength. And if you recall, for constructive interference, you must have crest and crest and trough and trough. For that to occur, for that pattern to occur, right, let's just do some revision here. If I have this, then I can have now my wave having the same in sync number of cycles, or I can have it differing by a whole number of wavelengths. Because even if I have a difference of a whole wavelength here, where one wave has started and traveled an extra wavelength compared to a second wave, then I will still have my crest and trough overlapping to create this. So even though they differ by a whole wavelength, it still allows me to have crest and trough constructive interference, right? So when you have for constructive interference, you must have a path difference in terms of whole values or whole multiples of lambda. So I can say n lambda where n is an integer, right, where I have a whole number of values. Now, consequently, if I look at destructive interference now, then I want crest and trough to overlap. So I would look at half a wavelength differences. So here I would want my second wave to be overlapping like this, so that the crest of one overlaps with the trough of the other and it cancels the wave. So I am looking at a half path difference. That is, the two waves must differ by half a wavelength. So for destructive interference, I have a difference in terms of m lambda on 2, where m is an odd number. Obviously, people wouldn't want m to be even, because then 4 on 2 will give me a whole number of wavelengths, which is the condition for constructive interference, right? So let's know that now. Let's go back to the question. So here you will find that now S2A prime is differing by half a wavelength. So at A prime, I would have destructive interference. In the same way, I would have S2A prime at the bottom be 4.5 and S1A prime at the bottom be 5. So now I would have a difference in half a wavelength, which is why on either side of the central maximum, my zeroth order, I will have darkness, which is destructive interference. So A and A prime would represent the positions on my screen of dark fringes. And because they are the first set of dark fringes, I call them the first order destructive. Okay? So now, let's look at another position. Let's look at first order bright. Right? So in the same way for first order bright, I am going to consider some position here. We're going to call that B, right? So S1B will obviously be more now. So let's say I have up to 5. I'm just saying 1, 2, 3, 4, 5. So I have 5 wavelengths from S1B because, and I will also have a B at the bottom here. So I would have had my A prime here, which was destructive, and then I would have had O being central, and now I have B, right? So now to go from S2 to B, it would be a whole number of wavelengths. So let's say I go up to 6 now. 1, 2, 3, 4, 5, 6, right? So now I have S2B, because S2 to travel to B is now greater than S1B. So this is 6 wavelengths and this is 5. So they differ in terms of 1 wavelength. So because they differ in terms of 1 wavelength, I have constructive interference at B. So then this will be first order bright. This will be first order bright. I would have had first order dark, first order destructive, and I would have my 0th order here. Now, if I wanted to show this a little more clearly, right? So this is A. I had S1, I had S2, right? You could show that you have a central maxima here, and I'm going to let purple represent destructive. So I would have had first order destructive. And after first order destructive, I would have had constructive. And then after that, I would have destructive. And then after that, I would have had constructive, right? So this would be first order, this would be second order. This would be first order, this would be second order, right? So now we can consider, let's say I am going from the midpoint here all the way here. I would have an angle theta 2, and then this would be the same angle here, theta 2. So these are my orders. This is n is equal to 2, n is equal to 2, this is n is equal to 1, this is n is equal to 1, right? In the same way now, if I am going all the way here to here, I would have had this angle being theta 1, which is the same as theta 1, right? So in fact, we could look at our separation of fringes delta y from the central maxima, right? And if you look here, you let this distance be d, right? So you let this distance be d. So here to here is d. And then you had this here is delta y, the separation of the first fringe from the central maxima, and you had the order. Then you can say now that it is a triangle. So you have tan of theta 1 is opposite over adjacent. So where is your opposite? Your opposite would be the fringe separation delta y, and your adjacent is d. So it's delta y over d. So therefore, we let theta, the assumption is theta is very small. So tan of theta is approximately theta, which will give me theta being delta y over d. So that's one equation. Now, if I look, and I'm going to draw back, I'm going back to my first diagram here. Right. So here you are seeing that the separation, it's a different color. The separation here is 1 wavelength, right? And we are going to find, we're going to look at this triangle here. I'm going to let A be the hypotenuse, we let this be right angle, and we let theta be here, right? So you have now a triangle where this is A, you have this being a wavelength, and you have theta. So you could say sine of theta is opposite over hypotenuse, which is lambda over A. In all of these assumptions, theta is small. So sine of theta is theta. So theta is lambda over A, right? A is the set separation. So equating the two, you have lambda on A is delta y over D. So lambda D over A is what is your fringe separation. And also leading from this formula here, we could say that if you want lambda is equal to A sine of theta, right? And what they have done is they have tweaked this formula to say that generically you will let your path difference, that is the difference between the two wavelengths from each slit to different points on your screen, which are representative of different orders, to give you different values or different whole number multiples of lambda. So that is n lambda, and then A is equal to D, right? So sometimes they let it be equal to common D, and more so when they use it in the context of n lambda is D sine theta. D really represents the spacing, all right? So you let this be equal to D sine of theta. And this is where your two equations originate. Now, I want to say that according to your new syllabus, you don't need to know the proofs. I have just kind of went through them because I wanted you to kind of get a conceptualization of it. So far, I think I've went into enough depth as possible in terms of the theory. Right? So I hope this video was useful. Is everything you need to know on diffraction.